me show you how to be a good breezy and change your predictions.
Janet, for listeners who are unfamiliar with INLA, so first, that stands for Integrated Nested Laplace Approximations, if I'm not mistaken. Could you give us an intuitive explanation of what that is and how it differs from traditional MCMC methods?
Yeah, sure. So in MCMC methods, what you essentially need to do is you need to keep drawing samples, and at some point these samples will come from the distribution you're actually looking to find. And then from those samples you can calculate things like the mean or the mode and so on. So INLA, what INLA does is it actually approximates with mathematical functions the posterior in its totality. So there is no sampling, waiting for things to arrive at the stationary distribution. You compute the approximation and then you have the posterior. So then you can from that get also the mean and the credible intervals and so on. So it's a deterministic method. It's not a sampling based method, which is why it's fast. But yeah, essentially that's kind of how it works.
Yeah, thanks. That definitely cleared that up. And I'm curious, actually, Haavard, when you started developing INLA, I think from your previous answer, basically you were motivated by making inference faster.
Yes.
But
yes,
also
yeah.
was that the main challenge you were trying to address, or was that also, were there also other challenges you were trying to address with INLA?
No, it was simply trying to, yeah, as said, first we tried to make MCMC work because at that time, early 2000, believed that this was the way to go, and then you're realizing it's not. At some point you make a switch. It's like MCMC is not going to work. It's never going to give us the kind of the speed that we need. And then we started on these approximations and working our way through that one. And that has been the goal all the time, you know, to make this inference for these kind of models fast. Yeah, fast is more important than, yeah, to make them quick. These have been to make them quick, kind of scalable in a way. And there are two types of scales. In a way, you can scale with a number of data points. We can also scale with a number of the model size itself. So these are two different things. And in the first version of INLA, we kind of scaled okay with both of them. And now in the second generation of INLA, then we scale way better, both with respect to model size and also the data size. So that's another redevelopment, but yeah, that's
Nice, yeah.
it's a second generation in that. So it was almost like a complete rewrite, and we bump the main methods. Yes.
Yeah, this is super exciting. I mean, well, we'll dive a bit more into that during the rest of the show, but yeah, high level, I think now we have a good idea of what that's helpful for. I mean, what's that doing? But I want us to also dig into the cases where that could be helpful. So, Janet, actually, I'm curious, how did you personally get introduced to INLA, and what drew you to this particular computational approach before we dive a bit more into the use cases?
Yeah, so I did my PhD in Bayesian statistics, and the main focus was kind of to write samplers for covariance and correlation matrices. So of course that doesn't go well, no matter which sampler you write. So I think very similar motivation, just there has to be kind of a better way to do this, even if you lose a little bit of generality. For specific cases, you have to be able to do better. And that's kind of where I started looking into approximate methods like ABC for the likelihoods, and there is VB and so on, and then INLA specifically, which like combines many many different approaches together, just to do things the same kind of accurate, but just faster.
Okay, yeah, I see. And actually, I read while preparing the questions for the show that latent Gaussian models are particularly suited to INLA. So I'm curious why, and also more in general, which cases are particularly appropriate and you would recommend to the listeners to give a try, to give INLA a try. So maybe Janet, you can take that one, and Haavard, if you have anything to complete afterwards.
Sure. So actually, a latent Gaussian model, this is the assumption on which INLA is built. So INLA is developed to do inference for latent Gaussian models. So if you do not have a latent Gaussian model, then none of the math will hold, because it's developed to do inference for latent Gaussian models. Okay.
So
then
can you maybe just briefly explain to listeners what a latent Gaussian model is?
Yes, I have to say, when I started at KAUST with Haavard, we had another colleague, Håkon, which was also Norwegian, and he did his PhD with Haavard. So it was me and them two. And at the first few months, it felt like they spoke a different language. Even though I had a PhD in statistics, I could not figure out what's latent Gaussian model and all these things. So I totally get this question when it comes up. So what is a latent Gaussian model? Okay, a latent Gaussian model is when you have data points for which you can assign a likelihood, and maybe the mean or some parameter in the likelihood will have a regression model. Okay, this regression model can contain like fixed effects, random effects, different components. And conditional on the model, the data is then independent, so that the likelihood is then just this product. So where the latent Gaussian part, sorry.
Yeah, no, exactly. I was gonna.
Yeah. So it's
give
like
you
a
the
GAM.
segue to go there.
It's like a GAM up to now, right? Like if you have a GAM, then the latent Gaussian part comes into the fact that all the fixed effects and the random effects should have a joint Gaussian prior. So if you can think of any random effect like an IID random effect or like a time series model. As long as they have a Gaussian joint distribution, then they will be a latent Gaussian model. So at first thought, it might seem like, oh, this is like a very restrictive class, but it's actually not. A lot of models that we use every day are actually latent Gaussian models. And even some very complicated models, like survival analysis models, they're also latent Gaussian models, a lot of them. If you do like co-regionalization, where you have spatial measurements at different locations, you can model them jointly, and this is also a latent Gaussian model. So it's really much broader than you would think initially.
Yes.
Yeah. Thanks, Janet. Super clear. That makes me think about, state space models, where most of the time you need linear Gaussian state space models. So that means latent Gaussian likelihood and Gaussian innovations. So like basically what you just talked about here, even though the structures of the models are different. And yeah, as you were saying, that may seem pretty restrictive, but that actually covers a lot of the cases. I guess some cases that can be more complicated are when you have count data.
No, they are the same. Actually.
Okay.
So the likelihood has no restriction.
You could have a binomial. Okay.
Yeah,
okay,
it can be any likelihood. It can be a zero inflated likelihood. You can have multiple likelihoods.
Nice.
Like you can do a multivariate data analysis, each data type with their own likelihood, as long as the latent part, so just the fixed effects and the random effect should have a Gaussian prior. But what you put on the data, that there is no restriction on that.
Nice, nice. Okay, so it's less restrictive than the classic Kalman filter then, because the classic Kalman filter only can take normal likelihood. So okay, yeah, that's really cool. And then I agree that's even more that's even less restrictive than what I had understood. Haavard, it looked like you had something to add.
No, it's Janet explained everything. It's of course, if you have one latent Gaussian model, if you have another one, you can put them together. So you also can do these kind of joint models where you share kind of effects. So all these kind of joint models is also covered. As soon as you have one, you can also do two, and then you can combine them together. So it's almost like, I think it's easier to classify all the models who are not latent Gaussian model. Is that it's a very surprising result in the sense of when you write it down, it looks so simple, but actually to make the connection from the model that you have to rewrite it in that form we need it's many struggle with that, because the form is so simple. You have some parameters like variances, correlations, over dispersions, and then you have something Gaussian, and then you have observations of the Gaussian, and that's it. So this structure covers almost everything that is done in practice today. You can say, okay, mixture models, this kind of thing is not in the class. Yeah, but they are not that much used, in the sense of in daily life of people who are working with this. Like more in research, yeah, you can do it. It's a little different, but in the practical life of people who do these things, it's not. So it's a very, very surprising thing.
Yeah. No, for sure. I mean, as soon as you start being able to handle normally distributed likelihoods and count data, you have, I would say, 80-90% of the use cases. Like mixtures are indeed, they are possible, but they are way less common for sure.
Yeah.
And actually, Haavard, you've been doing that for quite some time now, as you were saying. So I'm curious what you've seen as the most impactful applications of INLA, especially maybe at extreme data scales, because that's really where INLA shines.
Janet, help me out. You know this better.
Yeah, so I mean, we've had the World Health Organization has used INLA for some air quality control methods. We've had the CDC used INLA for like epidemiology. We've had the Malaria Atlas project use INLA to model the prevalence of malaria and to kind of help inform interventions and where they should be. And for instance, I mean, we are past COVID, but a lot of people still work on COVID. And I just checked quickly this morning, and there is more than 800 papers who used INLA for COVID modeling. So yeah, there's a lot of impactful applications, but on a very large scale, there has been applications. Recently, there is a paper by Finn Lindgren and others who've used it to model temperature on the global scale with lots and lots and lots of stations, and they can do a very high resolution model. So like Howard said before, the kind of modern framework for INLA that came like after 2021, it can scale now very, very high with data.
Nice, yeah. And actually, I'm wondering, like, when you say people are using INLA to model these data sets, what do they use? What's a package you recommend people check out if they want to start using INLA in their own analysis?
So the INLA methodology is implemented in the R-INLA package. So it's an R package. There is a Python wrapper, or soon there will be, or it is there, but anyway. So there will soon be like a Python wrapper where you can use INLA in Python. So
nice.
yeah, I think, most people just use the R-INLA package, and Haavard does a great job. There's kind of almost a new testing version every few days. So the development is very, very fast. Usually the package is faster than the papers. Like, we would implement something, and then a year later the paper would come out explaining what was changed. So users always have the latest version immediately.
Yeah, this is super cool. So the R-INLA package is in the show notes already, folks, for those who want to check it out. So yeah, check out the website. There are some examples in there, of course, of how to use it and so on. And if you guys can add the Python wrapper to the show notes, that'd be great, because I think, yeah, definitely that will increase even more your number of users. I know I will use that because I mainly code in Python. So yeah, like that's for sure something I will check out. Haavard, anything you want to add on that?
No, I think it's fine. It is what Janet say. But we are not on this C-run. We are not on this public repository, or the standard R repository, simply because the R code is just a wrapper. So inside there is a C code. It's a program that runs independently. And this is simply too complicated to compile on this automatically built system. So we build it manually and include it in the package. And for this, because it's contained in binary, then it's cannot be in this kind of public repositories. So we have our own that you need to kind of download from.
Okay, yeah, damn, that adds to the maintaining complexity. So thank you so much for doing that for us. I know it can be complicated.